Hello, so welcome to today's video. In this video, we are going to introduce the concept of the discrete Fourier transform. So the discrete Fourier transform is important primarily for because it is actually a very efficient to compute. So if you look at the DTFT, the problem with the DTFT is that it is actually defined for all values of omega, and computing it effectively, for all you can't compute it for all values of omega on a computer, but the DFT in fact is efficient to compute as we will see, and in fact the algorithm used to compute the DFT is called the fast Fourier transform, FFT. Okay? So in fact, people actually use the terms discrete Fourier transform and fast Fourier transform interchangeably. Actually speaking, the discrete Fourier transform is the actual transformation of the signal, while the fast Fourier transform is an algorithm to compute the discrete Fourier transform. And it provides us quick and efficient analysis of discrete signals, discrete time signals. Okay, so it's again like I mentioned, the FFT is being computed several times over on your smartphone or on your PC whenever you deal with practical signals like images, voice, and things like that. Reason is because it gives you a very nice way of characterizing the frequencies without having to go to the DTFT. And in fact, you can even perform some bits of processing using the DFT very efficiently. So let's actually introduce the DFT. Of course, there are some limitations and there's some restrictions on how well you can do it. But still, let us actually attempt to introduce the DFT in a simple way. So we are going to take a signal xn. Okay, and we are going to assume, make an assumption initially. We're going to assume that it has finite support. In fact, we are going to make a further restriction, that is, we're going to say define only for n is equal to 0, 1, 2, and dot, 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 up to m minus 1. In other words, we are going to consider an m length sequence. Okay, it is non-zero only from 0, 1, 2 up to m. Okay, of course, you can take even a larger kind of m than the actual definitions, but we will see that eventually. But let us take this. Now xn has finite support, so it's almost like this. Okay, so if you have, this is your n, so this is 0, this is 1, and this is m minus 1, and it is only here that you have defined, it's only here that you have defined the signal. Okay, it has finite support, it's defined only between 0 and m minus 1. Now, if you recall, when you did the continuous time Fourier series, you remember that whenever you take a periodic signal, you are able to express the periodic signal using a countable number of terms, the countable number of terms being the Fourier series coefficients. The similar way, we are actually going to define this concept of the discrete Fourier series. Okay, the discrete Fourier series, that is, we can express periodic sequences using sinusoids. Of course, rather than sinusoids, I'm going to put sinusoid in brackets. I'm actually going to use complex exponentials. Now this can be done. How? So here is what I'm going to do. I'm first going to take the periodic extension of this xn. Okay. So we are going to define x tilde n. Sorry, I should make it small n. Okay, let me make this a little more. okay, of xn. What does that mean? You take this xn, where is the selector? Okay, and you basically just take the periodic extension, meaning you just put it on over here, and you just keep repeating it on the sides, so it's like dot 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 dot, so that if this is 0 and this is m minus 1, then at m again it starts and goes to 2m minus and 2m minus 1, and similarly over here, and so on. So in other words, we define x tilde n to be x of n modulo m. So what does the modulo operation do? The modulo operation brings it back to a number between 0 and m minus 1 by doing a remainder operation. For example, if you take 7 modulo 3, okay, 3 2s are 6, 6 plus 1 is 7, that will be 1. If you say 10, or yeah, sorry. Let me make it 11 modulo 3. 3 3s are 9, 9 plus 2 is 11. So this is the remainder where you get when you divide 11 by 3. Now what is the advantage of the remainder? Whenever you divide a number by m, the remainder is 1 of 0, 1, 2, 3 up to m minus 1. So this modulo operation brings it back. Now you can naturally see that the moment I substitute capital M modulo m is 0, so you get back x0. When you substitute m plus 1, you get back x1, and so on. So this is the so-called periodic extension. Now you may say, why don't you start with periodic sequences directly? The reason we don't start with periodic extension is that in practical situations, you actually record, let's say, your voice or an image or something like that, and you have a finite length sequence. Whenever you have that, we are going to show that this periodic extension allows us to get an interesting property. We can make it into a sequence which is periodic. Of course, you may say, what is the practical relevance? Hold on for a minute. But this yields some good analytical tools. At least you can imagine that you can compute the periodic extension. At least you can imagine that that can be computed, right? Because it's just an extension. Now, this x tilde n has all the information of xn. How do you go from x tilde n to xn? You just take x tilde of 0 up to x tilde of m minus 1, that is equal to x0 up to xm minus 1. So this m is inbuilt information. We know that if you take the values of x tilde from 0 to m minus 1, you get back x. The rest are just duplications. So keep that in mind. So now the claim is that we can express x tilde n as summation, okay, k runs from 0 to m minus 1 x tilde k, notice that this is capital X, e power j 2 pi k by capital M for a suitable choice of capital M. Okay, in fact, I think in the textbook they use capital N. It's okay, but you can do this. So there exist complex numbers x tilde 0, x tilde 1 up to x tilde m minus 1. In fact, yeah, such that you can write x tilde n as a combination of these. This is actually a very reminiscent of the Fourier series. The Fourier series, you have something very similar. You remember, this is of course a finite summation. We'll see how that plays in. And this apparently can be done. How so? Let's actually try it for some particular cases. Okay. So let's say I take my xn to be delta n minus half delta n minus 1 plus delta n minus 2. Okay, this is the sequence 1 minus half 1. This is the sequence, and I'm going to take m is equal to 3. Remember, it's 0 to m minus 1, so I'm going to take m is equal to 3. Now the claim is that I can write x tilde n in this manner. How? So remember, x tilde n is actually x n modulo 3 because I chose m as 3. Now, can I express can I express my xn x tilde n in terms of x capital X tildes? Now for this, you must remember again, we must use the same trick we used in the continuous time Fourier series. We use the fact that the sequences e power j 2 pi k by n for different values of k's are orthogonal. How? Have a look. The claim is that x tilde n, this is the claim, and I will show you that this is possible, is I'll expand the summation above as x tilde 0 when I put k is 0 plus x tilde 1 e power j 2 pi by 3 n plus x tilde 2 e power j 4 pi n by 3. Okay, because I put k is equal to 2. This is the claim. Now I have 3 equations and 3 variables. Okay, so let us see how we can solve it. So if I put n is 0, I will get x tilde n, which is 0, which is 1 rather. 1 is equal to x tilde 0 plus x tilde 1 plus x tilde 2. If I put n is equal to 1, I get x tilde 1 is equal to x tilde 0 plus x tilde 1 e power j 2 pi by 3 plus x tilde 2 e power j 4 pi by 3. And finally, if I put x tilde 2, so in fact I can even write it in this way. 1 minus half 1. Okay, I'm sorry about that. I don't know why that happened. Yes. Is equal to, notice how I'm writing it. So this is actually useful. Whenever you have equations like this, it's useful to project them in the form of matrices. Now I will write 1. Okay, and so if you look right, I put n is 0, so I get 1, 1, 1. If I put n is 1, I get 1 e power j 2 pi by 3, e power j 4 pi by 3. If I put 2, I get 1 over here, e power j 4 pi by 3, and I will get e power j 6 pi by 3, which is again e power j 2 pi by 3, plus e power j 6 pi by 3. I'm sorry about that. E power j 8 pi by 3. E power j 8 pi by 3 is the same as e power j 2 pi by 3. Now the question is, when does this have a solution? It has a unique solution when this matrix is invertible. Now, is this matrix invertible? The answer actually is yes. In fact, if you find the determinant of this matrix, it will be non-zero. This I leave as an exercise to you. But there is something a little more interesting. This matrix has a special property. It's what is called an orthogonal matrix. Why is it an orthogonal matrix? If you take the dot product of any two rows or columns, you get 0. But remember, when you take dot product, you must take the dot product by taking the conjugate of one more. So let's take an example, okay? Okay. So let's take the first row and the second row. So I must say 1 multiplied by 1 plus first row and second row, right? 1 multiplied by 1 plus 1 multiplied by e power minus j 2 pi by 3 because I'm taking the conjugate plus 1 multiplied by e power minus j 4 pi by 3. Okay, this is equal to 1 plus e power minus j 2 pi by 3 plus, and remember, if I look at e power minus j 4 pi by 3, I can always just take, if you look at 2 pi minus 4 pi by 3, that leads to e power plus j 2 pi by 3. So e power by 3. Okay, so this is 1 plus 2 cos 2 pi by 3. Now cos 120 degrees is minus half, so minus half and half, so this is going to be 0. Similarly, if you look at these two rows or these two columns, 1, and if you do this, you get e power minus j 2 pi by 3, If you do z equal j plus 2 pi by 3, you get the same, you get 0. So in fact, this is what is called an orthogonal matrix. An orthogonal matrix, by definition, you can show that its determinant is non-zero. It is definitely invertible. Okay, which also leads me to the next point. How do you get back? Suppose I give you x tilde, suppose I tell you I give you x tilde n, find x tilde 0, x tilde x1, x2, x tilde 1, x tilde 2. If I do the reverse, if I give you, x tilde 0, x tilde 1, x tilde 2, how do you find x0, x1, x2? You can just invert this matrix and do the same thing. Okay, so why do we go through all this? So it turns out that this orthogonality is proof that this kind of separation, this kind of definition will always exist. That is, the way you must look at it is this. What is x tilde n? X tilde n is actually something like this. Okay, at 0, the value is x0. At m, the value is x0. Okay, at minus m, the value is x0. At 2m, the value is x0, and so on. Plus, at minus m plus 1, the value is x1. At 1, the value is x1. At m plus 1, the value is x1. Plus, and so on, till you get to the, I think this is minus m, this is 0. So you get, I think, till minus 1, the value is xm minus 1. At, I think, m minus 1, the value is x of m minus 1, and so on. So you are basically splitting your x tilde n into all places where it's x0, which is for n is equal to minus m, n is equal to 0, n is equal to m, n is equal to 2m, plus you're taking x1, wherever it is x1, that is minus m plus 1, at 1, at 2, m plus 1, 2m plus 1, 3m plus 1, and so on, and adding it up. That is what you're doing. Now, that means the basis which you're using to express, in other words, if you remember your linear algebra, you can actually express xn as, okay, let's maybe I'll write it in this way. So this, let's say x tilde is the same as x in this A region. So you can say, okay, this is equal to x0, okay, I'm sorry about that, multiplied by 1, 0, 0, 0, 0, 0, plus x1 multiplied by 0, 1, 0, 0, 0, 0 up to, this is basically an m length vector, okay, plus dot dot dot, plus x m minus 1 multiplied by, okay, these things have to be lines, 0, 0, 0, 0 up to 1, dot 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 1 in the last. So you are essentially expanding it in terms of 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, and these are actually like axes. Okay, you can actually express this at something like x0 along the 1, 0, 0, 0 axis, x1 along 0, 1, 0, 0 axis, and so on. It turns out that since this 1, 0, 0, 0, 1, 0, 0 is like a basis, it turns out that 1, 1, 1, 1, 1 and 1 e power j 2 pi k by, sorry, e power j 2 pi by n, or m rather, e power j 4 pi by m, dot dot dot, e power j 2 pi m minus 1 by m. It turns out that this is also a basis. You all remember this, right? Whenever we have like an x-axis and y-axis like this, right? You can always transform the axis so that, at 45 degrees, and you get new coordinates. How? Because these are orthogonal axes, these are orthogonal axes, you can always transform them. In the same way, you can think of 1, 0, 0, 0, 1, 0, 0 axis, and 1 e power j as axis, similarly 1 e power j 4 pi by m, e power j 8 pi by m, and so on, and you can say e power j 4 pi m minus 1 by m. Similarly for 3 times, similarly for 4 times, and so on. And the more important thing is these are orthonormal. So here the last one will be, here we'll have e power j 2 pi m minus 1 square by m, and here you have e power j, here you have 1 e power j 2 pi m minus 1 by m, and so on. Okay, sorry about that. Okay, these are also orthonormal, meaning if you take inner product of any one column over here with the column of that, then that results in 0, which means these are also orthogonal matrices. It's just like a rotation of the axis. Now, given that this is the case, what is the discrete Fourier series? The discrete Fourier series just says that rather than express your sequence in this using deltas, you can express your sequence, periodic sequence. Of course, using still does also. Okay, let's take another example. Okay, let's take another example. I'll take a simpler example. Let's take the sequence xn is equal to delta n. I'll say delta n minus delta n minus 1. And now, just for fun, I'll take m is equal to 4. Now, when I take m is equal to 4, then my sequence actually becomes 1, minus 1, 0, 0. Okay, I'm deliberately taking m to be larger. I can take it as larger, I can't take it as smaller. So the effective sequence will be 1, minus 1, 0, 0, 1, minus 1, 0, 0, repeated ad infinitum. Let us find x tilde for this. Okay, how do you do that? So once again, okay, you can solve equations or something like that, or you can find the inverse of this matrix directly. I'm just going to try to do something simpler over here. Okay, so delta n, this is like 1 minus 1 0 0, right? Okay, so let's see what we get. So we have 1 minus 1 0 0. Okay, let's construct this matrix. Okay, let's construct this matrix over here. This matrix consisting of these. Okay, I have 1 1 1 1 1 1 1. Okay, that part is clear. Okay, and then we'll have x tilde 0, x tilde 1, x tilde 2, x tilde 3. Okay, so now what comes here? E power j 2 pi by 4. So e power j 2 pi by 4 is j. Okay, I hope I have written it right. Yes. And over here, what do I get? E power j 2 pi. So it's like x tilde 0 plus here I have j, and here I will get minus 1. Here I will get minus j. Here I'll get e power j 4 pi by 4. E power j 4 pi by 4 is minus 1, 1 minus 1. Finally, here I will get minus j minus 1, and I'll get j. How do I get this? You can just take, it's like e power j 2 pi into 3 by 4. So you'll get e power j 6 pi by 4. You'll get e power j, you'll get the minus j directly. Okay, this thing you can work out. Okay, so let's now try to solve this. Okay, if you try to solve this, you can do one thing. You can basically just try to do it in a manual kind of fashion. Instead, I'm just going to open a terminal and I'm going to try to show you what we get. Okay. 3. So while we are at it, you can just quickly try to find the inner products. So this will be 1 minus j minus 1 plus j, which is 0. 1 minus j minus 1 plus j, again it's 0. So you're going to have this this inner product 0 being okay. Okay, so I'm going to import numpy, and here is what I'm going to do. So w is equal to okay, np dot array. Okay, so I'm going to say 1 1 1. Okay. 1 1. Okay, this is actually too much to do. So instead, we just want e power j 2 pi k by n and want an outer product, right? So here is the way I'm going to do it. So I'm going to say, okay, so this is the numbers 1, 2, 3, 4. I want e power j 2 pi k by n. So I'm going to say, okay, so this is what should come in the e power j 2 pi. This is what should come, right? So here is what I'm going to do. J 2 into np dot pi divided by 4. Now you see what we get, right? We get 1, 1, 1, 1, 1 j minus 1 minus j, 1 minus j. You get this, right? So you can basically see that we get this matrix. Now let's actually look at the inverse of this. So I'm going to call this W. So now I'm going to say, ordinal. Okay, I'm going to say numpy ordinal dot in W. Okay, if you see this is 2.5s over here. I'm just going to multiply by 4 to show you. So what happens is that you get 1, 1, 1, 1, 1 minus j minus 1 j and things like that. So if you invert this matrix and multiply it by 4, of course, then you get the same very similar looking matrix back. But this matrix has a slight issue. This matrix is actually going to be the Hermitian of the original matrix. Okay. The reason is because when you have an orthogonal matrix, its inverse is actually its transpose conjugate. Okay. So let's see what happens. So I'm going to invert W and multiply it by. So I have minus 1 minus 1 0 0. P dot array. I'm going to multiply it. So I put add 1 minus 1 0 0. Okay. So if we now interpret this, I get 0 x tilde 1, it turns out is 1/4 plus j 1/4. X tilde 2 is equal to half. Finally, x tilde 3 is 1/4 minus j 1/4. Let us interpret this now. That means my x tilde n should be, this is 0 for the constant term, x tilde 1 multiplies sorry 2 by n by 4, okay, plus 1 minus j by 4 into e power minus j 2 pi n by 4, because the this is like e power j e power 3 into 2 pi 6 pi by 4 is actually going to become minus, it's going to give you a minus 2 pi n by 4, and you're going to have plus half into e power j 4 pi n by 4. This 4 pi n by 4 can be written as minus 1 power n. Okay, so let's simplify this. So I'll get this half into minus 1 power n. Okay, and let's take the plus part over here. Plus, this is going to give me cos 2 pi n by 4 into 2. So half cos 2 pi n upon 4. Okay, and then plus, now the other part is going to e power j plus e power minus j is going to give me e power j minus e power minus j is going to give me sine. So but then I'll have a 2j over there and there's an extra j, so I'm going to say Now we have to check whether this matches the original sequence for n is equal to 0, 1, 2, 3. Okay, because it's obviously it's periodic with period 4. That is clear to us. We have to check for n is equal to 0, 1, 2, and 3. What happens when n is equal to 0, 1, 2, and 3? Okay, let's say n is 0. When n is 0, we get, I'll do a rough calculation, half plus half minus 0, which gives 1, which matches. Let's say when n is 1, minus half plus, now when you put n is 1, this is pi by 2, this becomes 0. And the second one actually comes in to picture, you get minus half, which is minus 1, which matches this. Excellent. When you put n is 2, you get half plus, and when you put in this 2, this becomes cos uh, pi, which means minus 1, half plus minus half, and then when you put in this 2, this becomes 0, you get 0, which matches the third one. Finally, when n is equal to 3, you get minus half, plus when n is 3, you get 6 pi by 4, where 4 pi will be related to pi by 2, will be 0, and when you put in 3, this is plus half, so you get 0 again. So indeed, we can express the original sequence periodic extension in this manner. Okay, great. What have you achieved by this? Notice that this e power j 2 pi by 4 is actually something like e power j omega naught n, which means that this expansion has something connected with the frequency. Okay, well, you say, oh, frequency, well, you can say something like cos and sine are actually infinite in length. Okay, they have infinite in length, and when they have infinite in length, then you can say the cos has this frequency, especially if omega naught is 2 pi by n, 2 pi of the form 2 pi by n or something of the sort, then you can do that, or a rational number into 2 pi by n, you can basically express something in frequency. But even when you do the periodic extensions DFT, which we have done, you get some notion of frequency. It turns out that this is actually connected to the frequency of the original xn, not x tilde n, xn. So xn frequency contents can be inferred by the Fourier series, discrete Fourier series expansion of x tilde n. Okay. So again, so what is the summary that you have to take away? You can express the sequence as summation of deltas or summation of complex exponentials when you have a periodic extension. Why did we have to do periodic extension? The moment you write e power j 2 pi n by capital N or something of the sort, it becomes periodic with period n. Even by doing the periodic extension, we will be able to say something about the frequency. That is the key that we're going to look at. Okay. Okay, so let's actually stick with this for one more minute. Okay, and let's do one more exercise. Okay, let's take this sequence. I'm deliberately changing to n. Now, what is the periodic extension of this? What is the periodic extension of this? This is actually very easy. The periodic extension is just to put the cos again and again. Great. Now, I am going to task you to find the DFT of this. For this, you should not have to go through the full thing, because this is cos 2 pi n by n. So this you can write as okay, okay. But how do you now interpret this? Okay, because we know that it is of the form summation. So this has to be of this form. Let's identify. How do you get 2 pi n by n? You get 2 pi n by n by substituting k is 1. So we get x tilde k is equal to 1. Next, How do you get e power minus j 2 pi by n? You can't get this, but we will make a small manipulation. We know e power minus j 2 pi n by n is equal to e power j 2 pi minus 2 pi n by n. Do you agree with me? Because you can always just multiply e power j 2 pi. There's no problem with that. So this gives me e power j 2 pi okay, let me be very careful. Is equal to e power, sorry, 2 pi n. I want to write 2 pi n. Yes, over here. This gives me e power j 2 pi 2 pi n minus 2 pi. Yes, 2 pi into n minus 1 into n by n. Which means that this corresponds to x tilde of n minus 1. So, sorry, this should be x tilde of 1 and x tilde of n minus 1 should be equal to 1. Okay. Now, as a preview, I am not telling you why. You can actually use the FFT function in NumPy to compute these discrete Fourier series coefficients. Really. So, as an example, let's say we take cos 2 pi n by 10 and find out what we must get. Then we must ideally get x tilde of 1 is equal to 1, x tilde of 9 is equal to 1, and the rest all, actually I made a mistake, there should be a half here, so I'm sorry, there should be half, and the rest all should be 0. Let's see whether that happens. Okay, I'm just going to use np.r to go up to, okay, this gives me 9, okay, so I chose n as 10, sorry, yeah, so I should choose this. Yeah, if I say n is 10, then it should go up to 9, because there are 10 sequences. I should just do np.cos 2 into np.pi into n into this by 10. Okay, so I have this sequence. Let me do this. Oops, I'm sorry. Okay, if I do np.fft.fft, okay, you can see that, okay, maybe I just I just do np.round. Okay, I'll just if you just observe this carefully, it's 0 here. Okay, you get 5. Okay, so I think yeah, I think there's a small I think there's a scaling issue. I'll get to the scaling issue in a minute. Okay, but the x tilde 1 is 5 and the x tilde minus 1 is 5. So my prediction was that x tilde 1 and x tilde 9 should be non-zero, and indeed that's the case. This 5 comes because there's an extra multiplication by a factor of 10. So it's like 10 by 2 and 10 by 2. So that is why. But the prediction is indeed correct that x tilde 1 and x tilde 9 are indeed the ones which are non-zero. Okay. So now what are we going to essentially, so, and if you want to do a sanity check, it's very easy. Okay. There's no sanity check over here. You can clearly see that my expansion is correct over here. Right. So in in that sense, okay, whenever you perform FFT or whenever you perform a DFT, discrete Fourier series expansion, you can always perform it for any finite length sequence with this definition. It is always reversible and invertible. Okay, you can always just start from the sequence, go to its e power j 2 pi summation x tilde k rotation, and come back. It's reversible. You can always use a matrix called you can call it the discrete Fourier transform discrete series matrix. That 1 1 1 1, that matrix you can construct and use it. This is about the discrete Fourier series. Now in the next class we will see how the discrete Fourier series can be used to arrive at a discrete Fourier transform. Discrete Fourier transform actually. Okay. Thank you.